Okay, questions?
For the first one on the front page, I was confused about the major product without rearrangement. Is the primary carbocation, if it doesn't matter with the
Yes, because I don't think you're allowed to draw primary carbocations, right? So I don't know what's the problem. Number one. Just hold it up. Okay. Okay, so this one we're going to react with H2SO4 and heat. Okay, so what's the first step in the mechanism? We're going to protonate the oxygen with the H+. So I'm going to form an oxonium ion. Okay, next step. What?
The water leaves.
If the water leaves, what kind of carbocation do I make? Am I allowed to do that? No. So the water can't leave at this point on its own. So what's going to happen is, this is my alpha carbon, right? If that's my leaving group, there's only one beta carbon, which means there's only one set of beta hydrogens. So what's going to happen is the beta hydrogen is going to leave as an H+, that pair of electrons is going to move down, and then the pair of electrons goes to the water, so that I lose, in the process, I'm going to lose an H+, and I'm going to lose an H2O, and I'm going to form the double bond then there. So that's going to be the final alkene product. Same thing as if this was your alpha. There's only, when you have a primary alcohol, there's only one beta carbon. So you're automatically going to form the double bond between the alpha and the beta carbon. But the water will leave with the H+. Because if it does it earlier, then you get a primary carbocation, which is not allowed.
You do a rearrangement where the carbocation gets shifted to a secondary?
You could, if I would have said, do this with rearrangement. When we form the oxonium ion, then the question is, then this hydride would do a 1,2. This hydrogen would do a 1,2 hydride shift. So it would come and add to that carbon while the water left. The difference is I would only lose H2O, and the hydrogen would shift over to the end carbon, so the plus charge would then be on a secondary carbon. So this one would be with rearrangement. And then the question would be, so then which beta hydrogen should I lose to form the final product? Because now I've got a new alpha carbon and new beta carbons. So which hydrogen would I lose to form the double bond? The beta hydrogen on the left or the beta hydrogen on the right? Left. So then I would lose that H+. So that would be my double bond.
Can you go over D on the last page?
D on the last page. Amanda, can you just hold it? You don't have to give it to me, just hold it up. Oh, okay. So in this one, what I was asking you to do was to give me the reagents that would be necessary to convert this chiral alcohol into the possibilities. So if I wanted to do this reaction with like retention, with retention of configuration, what would I use? I could use SOCl2. I could use PCl3 as well. So those reagents, first SOCl2 and PCl3, all they do is basically substitute an OH with a Cl. That's all they do. And when it's a chiral alcohol, they do it by inversion, or they do it by retention of configuration. So this would be, in this case, it would be retention. And then, if I didn't care about the chiral center, if I just wanted to convert this into a racemic mixture, so if I wanted this to be a racemic mixture, what do I need to do? I basically need to perform this mechanism through a carbocation. So in this case, HCl would give me a racemic mixture. And then if you wanted to do it by inversion, you would need to convert the OH into basically a tosyl ester. And so if we reacted this with the tosyl chloride, that would convert the OH into the tosyl ester, and it doesn't change the configuration of the carbon attached to the OH. So now if I brought in something like a Cl-, the Cl- would come in, and this would do an Sn2 mechanism, so that would undergo inversion of configuration, so that in essence the chlorine and the H we put the chiral carbon in. So that it would undergo inversion. So all I did in this problem was ask you to give me the reagents for the problem that I think is at the end of the first section, where you had to write the products given the reagents. So that's the three ways that we can handle this chiral alcohol. We can either convert it to a chloride with retention, make it racemic, or do inversion.
I just have a question for like the test. Can we just write tosyl chloride, or do we have to write out the whole?
That'd be helpful to write the whole reagent. What?
We won't lose points if we just write the name like as we want to, and then we try.
What do you want to do? So you want to, so now if you did this, if you said react that alcohol with showing the structure of the tosyl chloride, and then 2 said Cl-, that would be okay. But you got to write the structure of this. Because if you just asked, do I have to write the structure of that, and I said yes, will I lose points if I write just TOSLC chloride? Yes, you will lose points. Because my first answer would have been no. You don't have to write the full structure, but you do have to write the full structure.
Can you also just go through on D under the first part, the mechanism of inversion for the toxic chloride with the chlorine?
So it's the same thing. It's the same as we have. It's the same as we have here. So I'll rewrite this in the Sn2. In the Sn2 transition state. So if I'm reacting the chloride with the tosyl ester, my transition state would look like this. Chloride to carbon to O to the tosylate ester on the other side. And then on this carbon would have been the ring and the hydrogen in the methyl group. Okay. Something like that. And I probably don't have the exact stereochemistry right. This is the transition state you would have gone through. So what happens then is the chlorine just comes in. If this is a normal, Sn2 type of transition state, we're going to automatically undergo inversion of configuration. The chlorine's going to end up in the position opposite of where the tosylate ester was. So if I asked you to draw that, the key thing would be to go through the Sn2 transition state and make sure that the other groups are on the correct bonds. And more importantly, if it starts R, the final product's going to show in the S configuration or vice versa.
For questions such as part 2, the second component, it's a secondary alcohol and you want to create a trans alkene that's pentane.
So, which one is this? Okay, so we're going to form the trans.
Yep. For a question like that, you requested that we show the reagents. Would you want us to show the least number of steps? For instance, you'd be able to use SO4. That's kind of one reagent.
Right.
Versus 2 with like SOCO.
If I give you this problem and say go from there to there, there's how many different ways to do this? I mean, there's H2SO4 and there's heat. Or I could convert the LH to a chloride. So I could use PCl3 SOCl2, or since it's secondary, I could use just simply HCl. So convert it to a chloride and then use NH2 minus. Any of those would be correct. I'd have the same set only with a bromine. And that would be it. But there's how many different ways to do that? As long as you had a method that worked, that would be okay. Now, the one-step method is probably the best. But you could use any of those other reagents as long as they work. Because what I indicate is we have PCl3, SOCl2, or HCl. to convert this OH into a Cl. I could use PBr. I could use PBr3, SOBr2, or HBr, and convert that OH into a Br, and then use NH2 minus. So the bromine analogs of those of the Cls. The major product with rearrangements. So be on the front page. Okay, so we're going to do that one with rearrangement. Yeah, this one, there's an issue. But let's just go ahead and, what was it, HCl? Oh, H2SO4. Okay, so first thing I'm going to do is what? Protonate the oxygen so that I have my oxonium ion. And then what's going to happen next? We're going to have water leave. We agree with that? Why can water leave? Because it'll form a secondary carbocation. Okay? Rearrangement. What? Well, if I was going to rearrange, which hydrogen would I rearrange with? So this is your alpha again. This is your beta hydrogen 1, beta hydrogen 2. So am I going to rearrange by shifting the left beta hydrogen or the right beta hydrogen? If I was going to do it, I'd use the left. But what's our fundamental rule about rearrangement? I have to form a more stable carbocation. So if I shift this hydrogen over, then what happens? I get another secondary carbocation. So can I make that shift? No, I really can't make that shift. Now, somebody pointed out if I did make that shift, then I could lose that hydrogen and form a more stable double bond, which is probably what I was thinking when I wrote this problem. But I didn't think through the idea that the shift wouldn't occur to begin with. So what we have to think about is when you shift, it's going to cost you energy. And you better get that energy back by forming a more stable carbocation. In this case, I wouldn't get any energy back. And you might say, well, but then if you formed a double bond, you would form a more stable double bond than before, so wouldn't you get some energy back there? Yes, but these systems don't work that way. If you're going to do something and get an energy, you can't take a loan out. So the molecule can't take a loan of energy out to make the more stable carbocation to then get it back on the double bond. It's got to get it back immediately. And then I think then I said, well, but if we were at high energy, you might see a little bit more of that double bonded product form. And it does say H2SO4 in heat. So how much heat would that take? I don't know. I know our rules say you only make one shift, right? It's not like the carbocation can keep shifting down the chain until it finds someplace. But in this case, the shift would have to occur to form a more stable carbocation, and that's not it. So when I said to shift it, you can't. If you thought that was a trick question, if I do it intentionally next time, it is. But it was just one of those things, looking at the final product, okay, you get a more stable product, but we would never, I don't know that we would make it there. It would be an interesting reaction to get this alcohol, reflux it in sulfuric acid, and look for the presence of that double bond, because it would tell you that that mechanism is possible. And it very well may be. I don't know. I'm not doing that. I'm not doing that reaction unless I can buy that stuff, because I'm not making it. But that's how you would, that's what you'd have to do if you wanted to think about those kinds of rearrangements. And somebody probably has. So that one you can't rearrange.
Can you do E on the second page?
E on the second page. What's the product? What happens? I'm going to deprotonate the alcohol. So the NH2 minus is going to come in and deprotonate the alcohol to form the alkoxide and NH3. So you have to watch out for these reactions, because this was the whole setup of the last class. We can't use tertiary and we can't use NH2 minus to form a double bond from an alcohol. We got to convert the alcohol to something else and then react it with the bases. What else?
When looking at part 2, would you be able to postulate instead of like hydrochloric acid before using NH2 or just tertiary oxide?
Yes, if you convert the OH to a tosylate, then you can use the NH2 minus or the tertiary oxide.
Okay.
But you've got to convert the OH first.
Yeah.
And you could convert it to a tosylate, you could convert it to a chloride or a bromide. That's why there's so many different ways to do these different reactions. And any of them would be correct. This is not correct if you want to make a double bond. This doesn't make the double bond.
We do C on the front page.
C. Okay, so if I'm going to add something like HCl to this, again, first step would be, that's what I'm doing, right? I'm adding HCl. So first step would always be protonate the oxygen. So if I do this without rearrangement, the Cl minus is going to come in and kick off the water to produce the alkyl halide in water. Now you could have said maybe no reaction, but remember we in lab last semester, or when you've taken lab, we did take a butanol, protonate it with sulfuric acid, and use bromide to kick off the water molecule. It just took us like 45 minutes of reflux in order to do that. So you could very easily do this reaction. This would be classified as an Sn2 mechanism. Okay. So you could do that if you protonated the OH and then you wanted to do a rearrangement on it. What would have to happen is this is still my alpha carbon, that's my beta carbon. So my double bond or my hydrogen would have to shift over and kick the water off. So in that rearrangement then, the plus charge would be on the tertiary position, and that would be the hydrogen that shifted. And then for that molecule, the Cl minus would come in and add so that you formed the tertiary chloride. So for rearrangement, for these primary systems, if the H leaves and the water molecule leaves, you end up with a double bond, no rearrangement. If the hydrogen shifts and the water leaves, then you're going to end up with a carbocation, and then you're going to have your nucleophile add.
So is that one that says SN1 with rearrangement, is it SN1 just because it goes through a carbocation?
Exactly. So anything that goes through a carbocation is a 1 mechanism. Anything that doesn't is a 2. So this one was classified as a 2 because it did not form a carbocation. Oxonium ion doesn't count. Be on the last page. So we're doing, oh, give me reagents that will do that. Many reagents that will do that. There's many reagents that will do this. Give me one. H2SO4 and heat would be one set of reagents that would do that. What else? And H3PO4 and heat would also do that. What else? Okay, SOCl2. What's the SOCl2 going to do? Replace the OH with the Cl. And then you said react that with terse butoxide? So in other words, replace the OH with a Cl. or replace it with a Br. So I could use SOCl2 up here to replace the OH with a Cl. I could also use PCl3, or I could use HCl if I wanted to boil it. What about the base? So tertiary butoxide work? How about NH2 minus? Would it work? Would tertiary butoxide work? You're not?
Because the beta carbon is steric here.
No.
Would it still go there anyway? That's the only option.
Well, that's the critical part. If this is my alpha and this is my beta carbon with one and only one beta hydrogen, if it's going to eliminate, it's going to have to eliminate there. So I would think tertiary butoxide would be able to work. NH2 minus work? Yes? No? There's only one set of beta hydrogens. Actually, there's only one beta hydrogen, period. So any base is going to, that's the only thing you can deprotonate. So it wouldn't really matter what the base is either. It could be chloride, or I could change it over to a chloride. I could change it over to a tosylate. I could change it to a bromide. And then I could do tertiary butoxide or NH2 minus. Okay. So there's kind of theme to these problems. A lot of times it's the same stuff over and over again. And if you recognize that while you're doing it, okay, that's half the battle. Anything else? All right, today's reading assignment is on epoxides and ways to make ethers. And we've done a lot of and it was also how to make epoxides. But I want to talk a little bit about ethers and how you make them. So let's say that I take an alcohol and I deprotonate it to form an alkoxide. My first question would be, how do I deprotonate the alcohol to make the alkoxide? What reagent should I use? I could use NH2 minus, true. What else could I use? AC minus? Yep. A C minus like a Grignard reagent. Okay. And also an H minus would work. So if you're going to do a direct deprotonation, you can use N minus, C minus, or H minus. Since on my little mini periodic table I've got C, N, O, F. So if I want to make an O minus, I've got to use things to the left of the O, including the C and the H. Now there's actually another way to make alkoxides. Back in general chemistry, you learned that if you take H2O and you react it with sodium metal, what happens? It can be a very violent reaction. I end up making sodium hydroxide and hydrogen gas. That's a redox reaction. So if you react water with sodium, you'll make sodium hydroxide and H2. So I'm going to replace one of the hydrogens with an R group and react it with sodium, and I'm going to get RO minus Na plus H2. So I can get an alkoxide by reacting an alcohol with sodium metal. Depending on the alcohol, it may be, well, it just depends. The reaction's normally not as violent, except the alcohol is probably flammable now. Because what makes the water violent is the fact that if you get a spark, it ignites the H2 gas that's being produced. And that's what makes the big flame and the explosion. In this case, the alcohol would be flammable too, in addition to the H2. Right. So that's a redox reaction. So we can make alkoxides by reacting alcohols with sodium, or we could react them with potassium. And then that would give us, again, the alkoxide plus now potassium as my counterion. So if you want to make alkoxides the traditional way, the traditional way has been to make them with metals. And then just, have the reaction not get out of control by using small chunks of metal, not a big chunk. Right. So this violent, this one's not as violent. So if I've said, I think my favorite creative YouTube video on the explosion of sodium metal into water was they took a kid's kiddie pool and filled it with water and then got some Hot Wheels tracks. But if you don't know what that is, it's orange track that the little Hot Wheels cars went on. I'm of that age where we had those things. It would loop the loop in the whole 9 yards. They're probably still out there, but so you may take the sodium metal and you make like a little ship off of it, and then you run it down the Hot Wheels track so that it kind of hits the water, floats for a second, and then explodes. That was the most creative I've seen. Potassium, I wouldn't do that with potassium because it's even more violent. Cesium's even more violent than that. I've made alkoxides with all those metals. Cesium you have to do like in a dry box, which is like it's like a thing you'd see with like the gloves where you can like put the babies in, except there's no baby, it's just in argon atmosphere. And if there's any moisture in there at all, when the cesium metal gets cracked open from a vial that it's stored in, it turns bright red. One of my graduate students had that happen in a dry box. He's like, it's glowing red. And I'm like, shut up, it isn't my dry box. So it got really red and it dried out the dry box because it reacted very, very well. So this is a traditional way of doing that. Now, once you get to the alkoxide, we now have a species that is both strong nucleophile and strong base. It has both of those tendencies. Now, this is the second one of these species that we've seen this semester. Because remember, The alkynyl anion was the same thing. So if you want to make the whole purpose here is how do I make an ether? Take my alkoxide, react it with an alkyl halide in an Sn2 mechanism, and now I will end up forming my ether. Analogous to taking the alkynyl anion, reacting it with an alkyl halide to put the R group on the end of the C triple bond C. So my question is, what kind of alkyl halide does this have to be? I hear primary or secondary. Agree, disagree? I don't see anybody agreeing. I see very few people agreeing and disagreeing. Do we agree? In order to make this Sn2, it's got to be primary or secondary. This is one of the common ways to make an ether, is to do this Sn2 reaction. This one is called the Williamson ether synthesis. It actually has a name that goes with it. The alkynyl anion doesn't. But this is what we call Williamson ether synthesis. And all it is make the alkoxide and then react it with a primary or secondary alkyl halide so that you do an Sn2 reaction to get the ether. What would happen if I decided to take something like ethoxide and react it with this that halide? What would happen?
The secondary part next to it.
So I hear an E2 reaction being proposed. Agree, disagree? You're not getting any help.
They could do SF1 possibly, but I don't really think that that's what the major product is.
So you say E2. Agree? Nobody's agreeing or disagreeing. So I mean, nobody's telling you you're wrong. They're not telling you you're right either. What?
Wouldn't it be S? Would it be S in one B1? It would be the tertiary.
I mean, it could. What kind of halide is this? Tertiary. But what did I draw the analogy to here? To that one. And what would that do with the tertiary halide? What did it do in the homework problems from a couple weeks ago? It did E2. So you're right, it's going to do E2. So then if I had to write my final product, I'm going to say alpha carbon, beta carbon, another beta carbon. Isn't this really getting tedious? Always writing the alpha and the beta carbons? Well, I'll trade tediousness for right and tediousness to get points every day. But that's what it's going to happen. So then I'm going to look at this alkoxide and I'm going to say, okay, which one of these beta hydrogens is it going to remove? And I'm going to have to look at that alkoxide and say, well, it's this kind of alkoxide or it's this kind of alkoxide. What are my two choices? What are my two choices when it comes to bases in E2? I either have sterically hindered or small, not sterically hindered. So we said, what do we say about these? They weren't sterically hindered because the triple bond's linear. So what about an ethoxide? What do you think? Sterically hindered or small? Small. So if it's small, then what kind of, which double bond am I going to form? It's going to come in right and grab this hydrogen, that pair of electrons moves, chlorine leaves that way. So I'm going to form the most substituted double bond because the small base can go after any hydrogen. It's going to go after the one that forms the most substituted product. Okay. So what's my point? Let me think about that. What is my point? Well, I know what my point is. My point is if you know how this reacts, you know how that reacts. They're the same. All the issues that we talked about with alkynyl anions now exist with alkoxides. Primary, secondary, it's going to do Sn2 and make the ether. Tertiary, that's a strong nucleophile, but if it can't act as a nucleophile, it's going to turn around and act as a base. So these are our two molecules with the kind of split personality. They want to attack first. If they can't, what have I said before? They get angry. I haven't gone with the PO phrase, but they get angry, and then they grab the beta hydrogen and rip it off. That's what they do. Both of those molecules. So that's the second of those strong nucleophile base compounds that we have. Okay? So there's a few other ways we can make ethers, but we'll talk about those probably after the exam. So Wednesday, I will answer questions that you have. Hopefully you've gone through and started to catalog the reactions that you've had so far, as well as the mechanisms. If not, today's a good day to start. But on Wednesday, I will answer questions.